Okay, so Patricia said wonderful things about you all, and I was doing some other work during the lecture, so I was actually tuned in as well, and I wasn't really listening too hard, but
Yeah.
I did hear you all sort of participating and enjoying the wonderful person who is Patricia. She is a very good friend, and I'm very happy that you all got to learn from her. And I hope that there will be another time between now and the end of the course, or maybe several other times where she can come and teach again. And maybe some other tutors will also get a chance to teach you all some topics. So, people are asking, did I see the comment? I still have not seen the comment. I've woken up. I've woken up in the mornings, including this morning, and I did not see it. Last night there was a big cloud in the way, so no luck yet, but I will keep you all posted. So, thanks for asking. Okay, so Patricia talked about triangles, and this is one of her favorite topics. So I was very happy she could do that. And she mainly talked to you guys about triangle similarity and triangle congruence. And you all talked about how for triangles to be congruent, they have to satisfy certain conditions. And she made a very nice list of those conditions. And she asked you all, I remember, to repeat those conditions. She really wanted you to have these in your head. So she talked about the side condition. So if two triangles have the same sides, they're congruent. If two triangles have the same side, the same angle, and the same side, so if you have two triangles like this, and they have the same side, the same angle, and another same side, these two triangles are congruent. And usually congruence is denoted by this sort of equal sign with a squiggly sign on top. And also angle, side, angle, and angle, angle, side. So you could draw corresponding figures and all that. So these are the four big ones. But what is the one that doesn't? Oh, and there's also hypotenuse log for right angles, for right triangles. So if there's a right triangle here and there's another right, sorry, if there's one right triangle here and another right triangle here, and they share the same hypotenuse, assume this is a right triangle. They say they share the same hypotenuse and they share one leg. You know that these two are congruent. You have to realize that this really boils down to these other conditions because you're given that they're right. You're already given information about the angle. But anyway, these are the four main things that she talked about. And there is one that doesn't work, and it is SSA. This is one that doesn't work, and the easy way to remember is that the way I've written it is not the way some people like to write it, and the way some people like to write it is spelling a bad word. So, okay, so this one does not work, and there are counterexamples. Um, let's see if I can think of one. I'm actually looking through my notes here. I've taken some notes. If you want to see a counterexample of why SSA doesn't work, I feel like I should give it to you because we haven't really proved to you. Um, we haven't proved to you that these things determine unique triangles. Um, so let's see here. Give me a sec, people. Okay, here's a good counterexample. So, okay, so why does SSA not work? I just found this in my little notes here. SSA does. So say we had this triangle, uh, this big triangle. Oops, sorry, coffee is in the way. Sorry. Here we go. Why does SSA not work? Okay, I'm going to draw a triangle, and I'm going to split this into two other triangles. And I'm going to call this A, B, C, D. Um, so say that, okay, say I've drawn AC, this line to be equal to this line, okay? Um, and so we might be tempted at this point. Let's see, I think I need another line here. Um, I'm also going to draw an altitude AX. So I'm going to call this point X. Okay, so this is an altitude. An altitude is just a line that drops down to the opposite, from a vertex down to the opposite leg that creates a 90-degree angle. And at this point, we would be tempted to conclude that angle that triangle BAX is congruent to triangle CAX, right? BAX is congruent to CAX. Actually, sorry, that by SSA, but we would resist this temptation. Okay. So first of all, do people see that what I have here is okay? Well, okay, this is not a good example. Okay, I'm going to give you a counter example. So here BC is the base of this isosceles triangle, right? So I'm showing you why SSA doesn't work. BC is the base of this isosceles triangle. And the base has been extended to this point D, right? It's just some arbitrary point beyond C. And so the two triangles, so A, clearly from this diagram, DC, triangle ADC, and triangle ABD are not congruent, right? So in other words, ADC, that's this triangle. This triangle is clearly not the same as the entire big triangle, and yet they share, they satisfy SSA, right? So these two triangles satisfy SSA, the supposed criterion, right? Because they share AB, they share this side here, AB, they share, AB is equal to AC, right? So they share a side. AD is equal to itself, right? And an angle, and they also share angle D. So you see, side. They share this side. They also share this side angle. And then clearly this does not make them congruent. So this is a counterexample of why side angle does not work. Sorry, that took me a bit longer. I was not planning on saying this, so I was sort of like looking at my notes and like trying to figure out what the proof was. Okay, but I hope that makes sense. So side angle does not work, but these are the congruence conditions. And you also talk about similarity, and really similarity is more simple. All you need is that the ratios of corresponding sides to be equal. So if I have this big triangle and then this little triangle, these two things are similar if, I'll call these things B prime, C prime. If A over A prime is equal to B over B prime, which is C over C prime. And sometimes people call this like K, or like some scaling factor, right? So basically similar figures are just scaled up or scaled down versions of each other. Okay, so I want to review the quiz because I wasn't there for it with you. And the quiz results were fair, but I think when I looked at the grade distribution, it was like there were like a bunch of people who did really badly and then like more people who did really well. But I want to address the first crowd, okay? And don't feel bad if you did badly because that's why we're here. Okay, so two triangles ABC, and if you did well, also pay attention. If you have two triangles ABC and DEF, and they are such that they share this angle A equals D. And so what can be said about these two triangles? Well, the first thing I would do when I see, this is a classic SAT problem, okay? The first thing I would do is I would draw just a schematic of these two triangles, just to get a sense of the labels, right? Which angles are corresponding to which angles. So here's ABC and DEF, and they share this one angle. So what can be said? Well, it turns out that to show that things are similar, you need at least two, you need at least two angles to be the same. That's the AA criterion of similarity. So here you only have one angle that's the same, And similarity, keep in mind, is a more general, any two congruent figures are also similar, but not all similar figures are congruent. So similarity is a more general class of sort of, it's less rigorous, it's less rigid. I don't know what better way there is to say it's like squares and rectangles, right? Every rectangle is a square, not every every square is a rectangle, not every rectangle is a square. Similarly, every figure that's congruent is also similar, but every similar figure is not congruent. So anyway, so similarity is the more general criterion, and if things are not similar, they're certainly not congruent. And for things to be mirror images of each other, that means that they're congruent, so that's wrong. One is the same as the other, only rotated. Well, that's the same thing as congruence. So the answer is nothing can be said. So any questions about this question? No. If two triangles ABC and DEF are such that side AB is equal to DE, so I'm going to draw two figures, and I'm going to ask this time for someone, oops. Okay, that's good enough. A, B, C. I'm going to ask for someone's answer this time. Okay, let's see. Who knows? Let's see here. I'm going to call on. Okay, I don't want to call on anyone, but if you know, can anyone tell me how to do this? What can be said about these two triangles if they share this side and they also
They're similar?
They're actually not similar because remember, similarity requires two angles to be the same, not two sides to be the same.
Congruent?
No, they're actually not congruent either, because remember, our conditions for congruence, besides HL, which is not applicable here because we don't have right angles, besides HL, you always need three pieces of information, right, to be shared. And here you only have two. So can anything be said?
No.
Nothing, yeah, nothing can be said because, yes, because the angle is not known. And you can think of, you can draw two triangles that share two legs in many different ways. The third leg, if it's free to, you can have this being the same as this, and you can also draw a more extreme triangle, so these things are the same. So two sides by themselves do not bound a triangle, so to speak. They don't determine the characteristics of a triangle. You need an angle in between to determine, or you need a third side. So yeah, so nothing can be said here. So this is a little counter example, okay? You can see that clearly this is not congruent to this. Okay, how about this one? Someone else, someone new. If two triangles ABC and DEF are such that sides A, B equals DE, AC is DF, and angle B is E, what can be said? So, sorry, my pictures are bad. Anyone, what can be said? You don't have to wait for me to draw these things.
They're congruent?
They are congruent because, let's be careful, because this could be the SSA condition, right? Which is not a real thing, but let's draw it out. So AB is equal to DE, AC is equal to DF, and angle B, hey, look, this is exactly the wrong condition. This is the SSA condition, and we gave a counterexample as to why that doesn't work in the beginning of this lecture. So nothing can be said here. Again, so you have to be careful, right? Just because you see an angle and angle, like I also, when I saw angle side, or side angle, I assumed that it was going to be in the configuration of SAS, but it was not. It was the bad condition. And again, the easy.
How do you know the difference between?
How do you know the difference?
SSA.
Yeah, here's for example, this is SAS. See, where the angle is between the legs, the sides. See how the angle is, yeah, it's sandwiched in between the sides. But the other condition would be like, if it weren't this angle that were equal, but maybe this angle. See, now the angle is not in between the sides. And we gave this counterexample at the beginning here. I'll just go back to it. Yeah, we showed that in this case, we showed that that this shaded triangle in red is not congruent to the bigger triangle shaded in blue, even though they share this one side, right? S. They also share this side, which is equal to this side, right? So they share that side, and they also share this angle. So this setup satisfies SSA, and yet obviously this red small triangle is a part of the blue triangle. In fact, it's not even, it's not even the same area as the blue triangle. Okay, so hope that makes sense. If two triangles ABC and DEF are such that AB, okay, so I'm going to draw this again. Someone tell me what they think. Okay, so AB is equal to DE, AC is equal to DF, and angle A is D. Now, which configuration do we have?
Congruent.
Yeah, this is SAS, right? So you have the side, the angle sandwich in between, and the side. So this is that they're congruent. Good. So it's really about visualizing. Like I would not just be able to look at the letters here and tell you the answer. I have to draw it out. I don't have the ability to visualize that in my head. Okay, if two triangles, ABC and DEF are such that AB, okay. By the way, I'm drawing really generic triangles and they all look equilateral, but generally it's good not to do that. It's sort of assume, anyway, it doesn't really matter in this case. Okay, so here we have AB is equal to DE, angle C is equal to angle F, and angle B is equal to angle E. No, I'm using different symbols to show that these angles are equal, like a angle sign with a line through it, just to show that it's B equal to E and not B equal to F, for example. Okay, can someone tell me what's the answer to this question?
Congruent.
They are, and why?
Because it's angle side.
Mm-hmm. Right, angle side, and you can see that is a condition that Patricia talked about that satisfies congruence. Here's your angle side. Great. Any questions? We're kind of blazing through. So these were the frequently missed questions on the quiz. There was also a question about like Minkowski space, which I did not even count. I didn't even assign a point to it because that's not on the SAT, and it's also just I just wanted to see if people were paying attention 2 days ago. So about half the people got it. Minkowski space, time in Minkowski space is not measured in seconds. It's measured in meters. It's measured in distance, which is the same units that are used to measure distance, right? So time and distance are not distinguishable, so to speak, in Minkowski space. And there was also a question about non-Euclidean space and whether triangles in non-Euclidean space have to add up to 180 degrees. And most people missed that, I think, or maybe about half the people got that. In non-Euclidean space, in other words, non-Euclidean just means curved space. And in curved space, you certainly don't have to have triangles, in fact, that add up to 180 degrees. And I'm going to share I was going to draw a diagram, but I think the best way to do this is to share my screen. Let's see here. There's a great diagram of, if you try to, generally, when you try to like go from, say you're, here you go. Okay, so here is a triangle where the sum of the degrees is, clearly greater than 180. It's 230 here. 180, this is 180 plus 50, that's 230. And yet it's a triangle and it's on the surface of the earth. And the reason you can do this is because you're not on a flat space, right? So you can have two right angles right next to each other. You can even make it even worse. You can make a 270-degree triangle if this angle here were a right angle, right? So it's very easy to show that on curved space, you can have a triangle that's not 180 degrees. And for our practical purpose, if you're driving from Dallas to Houston even, which is a significant arc of the earth, it still doesn't really matter because that distance is much, much, much less than the entire circumference of the earth. And so, so angular measure is still very Euclidean for our day-to-day purposes. But for things like plane flight, and they actually do have to account for the fact that the Earth is curved, right? When they're traveling significant arcs of the Earth. Okay, anyway, that was just an example. Okay, so really, if no one has any further questions about triangles, I'm going to move on to today's topic, which is circles. Okay, so does anyone have any more questions about triangles? We're going to return to triangles on, what is today, Wednesday? Tomorrow, we're going to return to triangles a bit more and talk about them a bit more in depth. But today's topic is circles, and that is really exciting because circles are, I think, the most important shape in nature. Because what is a planet? What is an orbit? What is a wave? We talked about sine and cosine, right? Remember how sine and cosine is just a projection of your angle on the circle on the y-axis, right? Sorry, it's a projection of where you are on the angle is on the x-axis. Your position on the circle in one dimension is either sine or cosine, depending on whether you're looking in this direction or this direction. Cosine is your projection of your position on the circle in this direction, the horizontal direction. Sine is the projection of your position on the circle in the vertical direction. That's really all that is. And so all the waves of nature are based on circles, actually, and things in nature obviously follow circular shapes, or close to circular shapes, and the generalization of a circle is a sphere, so on and on. And circles are very beautiful because they have many properties that nature likes. So formally, it is the set of points equidistant from one point C, the center. So I would write this down or memorize this, and it's sort of obvious if you think about it. It sounds very formal, but the set of points that's equidistant from one point, well, here's my point C, the center, and if I just pick a point, right, just a first point, well, the set of points that are all equidistant to C, so here's my distance D, and so to create a set of points, to create the circle, I would have to pick all the points that are also equidistant, that also are a distance D from this point C, and I would realize that all of these points are a distance D. I can't pick a point that is not along this arc, right? All these distances are D. I can't pick a point out here because this is greater than D. I can't pick a point inside because that's less than D. So basically, yeah, all of the points that are equidistant from a center C defines a circle. And so this is a bad circle. Anyway, my points didn't fit the circle, but you get the point. No pun intended. Okay, so all the conic sections have similar definitions, like an ellipse, for example, which we talked about briefly what an ellipse was, but an ellipse, okay, so this is not on the SAT, but an ellipse has two, basically what are called foci, but that's plural of focuses, a focus, right? You can call them focuses if you want. So these are your two foci or focuses, and the definition of an ellipse is the set of points such that the sum of the distance from each of the foci, from each of, from this focus and this focus, the sum of that distance is the same. So in other words, if this is A and this is B, A plus B is the same as here where you have A and B. So in other words, an ellipse is, that's sort of the definition of an ellipse. The definition of a parabola is, there's a property of parabolas where they have a focus and something called a directrix, or I think they denote this by P or maybe D, but it's called directrix. And I think in algebra 2, some of you might have learned this. But the definition of a parabola is that the sum of the distance from the it's the distance from the focus that's equal to the distance of the directrix. So the parabola is the set of points that satisfies that condition, where the distance to the focus equals the distance to the directrix. So all of these distances are equal. So anyway, all the conic sections have their own verbal definitions, and the definition for the circle is a set of points that's equidistant from the center point. And there are some important terms that one should know when dealing with circles, and I think much of this will be review, but some of it might be new, especially towards the end of our list. And I'm going to call on people to get some participation. So this should be very rudimentary, but I'm going to call Ria. Your name was the first name I saw on the participation list. Can you tell me what the diameter is of the circle? Ria. Okay, no word. Robin. Nothing. Soliana. Diameter.
Isn't it 2 times the radius?
It is 2 times the radius. Okay. It is 2 times the radius, but that's more of a, that's not really a definition, because now you're relying on the definition of radius, which we have not.
Can I say?
Go ahead. Anyone.
The diameter is the middle from like the outer, I guess. Like dry, yeah, and then go the whole way. It goes the whole way.
Right. So it's the greatest distance across the interior of a circle, right? So this is not a diameter. This is not a diameter. You can get really close to this diameter, but that is not the greatest distance across the interior of a circle. You have to find the greatest distance. And how many diameters are there of a circle?
1.
How about?
Infinite.
Yeah, I think what you're right that the diameter is just one value, you know, so this length is equal to this length, but I can draw the diameter an infinite number of ways, right? I can draw it as many times as I want, and as many, you know, you got what I mean. Okay, so you can draw the diameter however you want, but it only has one value, and that is the greatest distance across. And the radius, as someone wisely said, the radius is half the diameter, or in other words, the diameter is twice the radius. So the diameter is the more natural quantity because it has this property of being the greatest distance across the interior of the circle, but the radius, okay, guys, let's focus on the math here, not AP exam scores. Even if this is a review, okay? The radius is just half the distance of the diameter, okay? The circumference, okay, let's see. I'm gonna call on Adi.
The whole circle.
Yes. Okay. The whole circle, what does that mean? I mean, can you explain
Like
that?
the entire exterior of the circle.
And it's
like-
a measure of what? Angle, distance, volume, area? When you say the whole circle, that's not a mathematical definition. Adi.
Sorry. Okay. So like the mathematical of the circumference.
No, but okay, when you say the whole circle, that's just a visual thing. Like, what about the
Like-
whole circle?
Like it's the enclosing boundary of the entire like circular curve.
Okay, so that's actually, I know what you're going for, but when you say it's the enclosing boundary, you're referring to a shape. You're not referring to a number. The circumference is a number, right? So what is that number?
Oh, 2 pi r. I was.
No. Sorry. Okay, so you're right. You're right. But okay, this is a fine point. But
The
when
perimeter.
yeah, that's more like it. Okay, so so all of these things are dimensionful quantities. So diameter has the dimension of distance, or I'll call it meters. All these things are. So when you say the whole circle, you're not referring to the dimensionality. You're not referring to the physics of what the circumference is, right? You're just saying the whole circle. Okay, well, what is that? Like, I have a picture of a circle in my mind. Okay, anyway, I'm kind of picking on you, but with the circumference is the distance the distance around the circle. So perimeter is fine. Yeah. Anyway, okay, I don't mean to pick on you, but yeah, the more precise you can be, the better. Okay, so can someone else tell me what is area? Let's see. I'm gonna call on Aditya. What's the area? Just like visually.
Just the area inside that
Yeah.
enclosing boundary.
The area inside, yeah, so it's just this entire thing. And what are the dimensions?
Meters squared or whatever, distance squared.
Yeah, meters squared or distance squared. Okay, good. Can someone else tell me what a chord is of a circle?
So a chord is like basically it's just a line that doesn't go through the center of the circle.
Yes, and actually, generally, it can go through the center of the circle. The diameter is a chord. It's just a special chord. But any general line that goes from one end of the circle to the other end of the circle, to any other end, to any other point on the circle is a chord. And so a chord intersects the circle twice, just like any line. Okay, that's not true. There are lines that intersect the circle once, and those are tangent lines, and we'll talk about them. Okay, good. So a chord has, we're not going to really get into it, but chords, two chords become really interesting. Like you can measure arcs and stuff of circles using, okay, anyway, I'm getting ahead of myself. But what is an arc? What is an arc of a circle?
So if a chord is a line on like the inside, then an arc is that like corresponding line on the outside. So that line that you just drew, the line, like the curve above it or the curve below it could be an arc.
Yes, good. So an arc is, and okay, so now Audie, I'm going to pick on you again. What is the dimensions of an arc? This is sort of a trick question. Is it meters or meters squared? Do you know?
Wouldn't it be like degrees?
It actually is degrees. Yeah. So this is a trick question. Technically, the dimensions of an arc is the same as the dimensions of circumference, right? Because that's what you're measuring. You're going around. But mathematicians define the arc in terms of degrees, and they don't even do that. They use radians. It's actually
they use radians.
Yeah, the arc is actually dimensionless. They identify, and sometimes you'll see in math textbooks when people write an arc. So say that this is A and B. The notation is AB with a curve on top. And they'll say that this equals, say this is 5, I don't know how many degrees this would be. Say that this is, 330 degrees. It's almost all the way around the circle. They would put this circle above the equal sign to show that they're identifying an angular measure or a measure of length with an angle. Okay, so this is just a notation, this equal sign with a circle on top. Okay, good. Thanks, Adi. Okay, so a secant line is similar to a chord. It's generally just a line that goes through the circle. A chord ends a chord is a line segment and it ends at the endpoints of the circle at the 2 points it meets of the circle. But a secant line is just a more general line that just passes through generally 2 points of the circle. And a tangent line is a line that only touches the circle once. So it just grazes the circle and it goes on forever. So tangent lines, in a sense, are more special. Okay, and I don't know if I'll prove this to you. I haven't really thought about the proof, but tangent lines, this is important for the SAT. Tangent lines, if I draw a tangent line here, pretend it's touching the circle, tangent lines are always perpendicular to the radius. The radius formed by the point it's touching, right? So no matter how you draw a tangent line, here's another tangent line. This is always going to be perpendicular to this radius. I'm thinking if it's worth proving. Probably not, because we have to develop the notion of arc, which I think we're going to do at the end of the lecture. But anyway, tangent lines so this is worth knowing. Tangent lines are always perpendicular. Okay, good. So now we have this basic vocabulary. So now let's actually talk about the meat of this topic of circles. We have a bunch of words to describe it, but let's apply these words. So it turns out that early people, I talked about how geometry is going to be a bit of a trip back in time, and this is one of those things where early people looked at the circumference of a circle. They would take a piece of yarn, just like a piece of string or whatever, and they'd wrap it all the way around the circle, and they'd count out sort of how much distance they covered. And then they would also take that piece of yarn and they would take the greatest distance across the interior of the circle, which is the diameter, and they would divide those two numbers. They would do other things. They would multiply those two numbers. They would add those two numbers. And someone decided, what is the ratio of those two numbers? What is, in other words, the ratio of the circumference to the diameter? And they found that the ratio from the circumference to the diameter is not a number that can be counted. It was a very strange number. And that number is pi, is what we know of today as pi. So they saw that you could do this for any circle. You could have a tiny circle. They would all gather probably around like a fire or whatever and draw a little circle and, like do the circumference, do the same experiment, measure, put the piece of yarn around the thing and then measure the diameter and divide those two. And they would find every time, no matter how big your circle, they would always find that ratio to be pi. And so people had different names for this, but the Greeks, used their letter pi, which looks like this. Make sure that it's not, you can just write it like this, which is how I did for a long time, but later in your math career, you'll find that this refers to a different thing. So that's why I draw it with this curved lines to show that it's lowercase Greek pi. Okay, and note that this is also, because diameter is is twice the radius, that this is the same thing as circumference divided by 2 times the radius. So this number they found to be this very mysterious number that doesn't seem to have any pattern in its digits and so on and so forth. So they could not write pi as a ratio of 2 rational numbers. Either the circumference or the radius would be irrational as well, causing pi to be irrational. And it's one of the most important numbers in math, so do not write pi as 3.14, right? Do not try to approximate pi. This is very middle schoolish. And actually, I had a grievance from our tutor, Gabe, who said on the last homework that was due last Friday, that people on the section where you're having to convert from degrees to radians and radians to degrees, that when people were writing pi, they were writing 3.14. So say I asked you to convert 180 degrees to radians, people were writing that this was 3.14 radians, which is close, but it's not correct. It's actually pi radians. So there's a big difference between 3.14 and pi, and that is the fact that 3.14 is a rational number and pi is an irrational number. So anyway, this was a small complaint that Gabe had, and he wanted me to tell you. Don't approximate pi, just write pi. That's why we have a symbol for it. And the history of pi is rich, and we're going to talk a bit more about that. But first, I'd like to knock out some of the actual math, right? What do you need to know for the SAT? Well, definitely what you need to know is how to find the circumference if you're given some radius or some diameter. So this is actually the definition of pi, and so I would write 3 bars, right? I would write 3 bars denoting that this is a definition. But this has become almost like a formula to us, that the circumference is 2 pi r or pi d, right? This is almost a formula. It's not, this is actually the definition of pi. And this is what you really need to know for the SAT. So if you're given the radius is 1, right? Find the circumference if radius is 1. Well, I would just plug this into this formula, pi d, which is 2 pi r, and r is 1, so then the circumference is 2 pi. And this matches our intuition of when we talked about how there are 360 degrees in a circle and how that equals 2 pi radians, right? We were assuming that we were having a unit circle, a circle of radius 1. Okay, can someone else tell me, find what the circumference is of a circle given that the diameter is 1 over pi squared? Let's see. Solina, your name was the first I saw on the list. Can you tell me what the circumference is of a circle given this diameter? No. Nishan, can you tell me what the circumference is given this diameter? No. Matthew, can you tell me what the circumference is given this diameter? No. Okay, this is really frustrating. I depend on you all. It's 1 over pi. You don't have to tell me the answer. Just turn on your microphone if you have your microphone and let's talk through it. That's really what I want. Okay. Anyway, how would I do this? I would say that the circumference is, again, I would use this. I'm given the diameter, so I'd use this formula, pi d, and I would put in d as 1 over pi squared. And here I have this, and you know that one of the pi's will cancel, giving 1 over pi. So don't let the numbers confuse you. Just because you see a pi, don't get scared. Just use the formula and everything should work out. Good. Okay. What is the diameter if the circumference? So this is a slight twist to the problem. What is the diameter if the circumference is pi squared? So I'm not going to wait for people to do this. I'm going to write the formula, pi, the formula, so to speak. It's really a definition of pi. But the diameter, first of all, I need to solve this equation for d, and that's ridiculously trivial to do. You just divide by pi on both sides, right? And now I'm given the circumference, so I'm going to plug that in here. And so it's pi squared pi, and so the diameter is just pi. Okay, so does this make sense? So you have to be able to manipulate. This is a linear equation. It's a trivial equation to manipulate. There is not even a plus c. So you know what I mean. There's not even a y-intercept, so to speak, of this equation. But you should be able to write c is pi d, c is 2 pi r, and then r is c over 2 pi, and d is, so all the iterations, d is c over pi. Okay, good. So I want to talk about famous approximations of pi, and this is a bit of a historical aside, and it's very interesting to see how people have evolved in their definitions, and these are worth knowing. These are good things to be able to talk about to your friends. It's impressive. So I am going to quiz you on these three things today, mainly identifying who thought what. So the ancient Babylonians, I should say, not the modern day Babylonians. The ancient Babylonians thought that pi is 3. And this was also reflected in the Hebrew Bible, in the Old Testament. The value of pi is proclaimed to be 3. And this was a humble estimate, that people used to think that when they took the circumference and they divided by the diameter, that the extra digits that they were getting were sort of not desired, because people in ancient days and antiquity used to think that these real, these perfect numbers and perfect ratios were very beautiful, that people, especially people like Pythagoras, who was after the ancient Babylonians, but these people really found beauty in ratios of rational numbers. That was redundant, but rational numbers are numbers that can be defined by the ratio of two integers, and they wanted pi to be defined as a ratio of two integers, and so this is a ratio of 3 to 1, and so they just said, okay, let's let pi to be 3. It was more of an aesthetic choice. They knew that it wasn't 3, but they approximated pi to be 3. But if you look at ancient Babylonian structures and architecture, the ruins that remain, you'll find that their constructions of circles was not perfect because of this approximation. In fact, it was far from perfect. They had to, whenever they planned for buildings and stuff, they would use this number, and then they would always have like a shortage of supplies because it wouldn't be enough to go all the way around the circle. So sort of humorous, and we laugh at them today, but that's what they thought. Then Ptolemy, who was much later, a great astronomer and mathematician, came out with this ratio. Earlier ratios were like 22 divided by 7. I have a feeling many of you might have used this. I think it gives pi accurate to 2 decimal places. Accurate to 2 decimals. But it's not quite, it's not quite there. And then Ptolemy came out with this nicer number, and keep in mind this is a ratio of 2 integers, therefore it's supposing that pi is a rational number, which is not true, but this was a more successful approximation accurate to 3 decimals that was very successful at the time. Then thousands of years passed, and the invention of calculus came about, and finally it was possible. So between this and this, I'm taking a huge gap in history. People made thousands of other approximations of pi as a rational number, but when calculus came about, it became possible to write pi or some pi by error of some factor. So like pi over 4, that's basically pi just scaled by 4. It became possible to write pi as a pattern of numbers, as a series. This is called a series in math, that is very easy to sort of follow. You can see that this is what is called the alternating odd harmonic series. It's alternating because it's only because the sign is alternating. Here you have plus sign, minus sign, plus sign, minus sign, plus sign. So that's why it's alternating. It's odd because all the numbers are odd. It's harmonic because the harmonic series goes like this. This is called the harmonic series. It's one of the most famous series in math. Anyway, the harmonic series by itself does not converge. That's worth knowing. But if you added up all these numbers and you went to infinity, that number does not close off. It diverges. Anyway, so yeah, so you exclude the even terms, and then you alternate your signs, and you get pi over 4. And the seniors are going to find out that when you expand the trigonometric function arctangent or inverse tangent, when you at the end of your calculus course, you're going to do some Taylor expansion, what's called Taylor expanding, and this is a beautiful part of the course, probably the best part of all of calculus in high school, and you'll find that the arctan of infinity is pi over 4, and so when you Taylor expand this thing, you'll get this value. Okay, great. So this is called the Leibniz formula. And it's amazing to see, there's a great Wikipedia page, and I'll send it in the chat. It's amazing to see the approximations of pi. You can see in the days of the Babylonians, 2000 BCE, the number of the amount of accuracy, which is measured here by the number of decimal places, was stupidly low. And this is like Ptolemy, and this is keep in mind, this is a great example of a logarithmic plot, right? See how this is not a linear plot. So this is also relevant to our course for other reasons, because we talked about logarithmic graphs and logs. Anyway, you can see just how ridiculously, this is sort of the dawn of the computer age, 1950, and you can see how ridiculously accurate our approximations have gone. And it's very entertaining to read this Wikipedia page that I'm about to send you. Read it after the class if you want. It's amazing to see like what people have approximated pi to be these days. I think like we're in the trillions of digits now, people. And in fact, January of 2020, someone approximated pi to be, I think, like, let's see, I have the page open. It's just amazing. Like, anyway, I can't find it now, but yeah, in the trillions of digits using supercomputers and such. Anyway, what is the area of a circle? You all know that this is pi r squared, right? Off the top of your head, this is like, if you go to elementary or like middle school in the United States, like, or anywhere in the world, you would know this off the top of your head. But how can you show this? Has anyone ever shown to you that this is true? And most people don't even see why this is true until they take a calculus class. But I am going to try to show this to you in a very simple way without using calculus. And the way I'm going to do that is by appealing to your understanding of the area of a triangle. We know that the area of any triangle, given its base and height, this is something Patricia talked about yesterday, given a triangle's base and height, the area of a triangle is 1/2 base times height, 1/2 BH. So if I split this circle up into an infinite number of triangles, but for now I'll just do a finite number of triangles, and I took each of these pieces, so watch, I'm going to use a different color to make this clear. Here's one piece. I'm going to put it here. Sorry for if there's noise in the background. I don't know what's going on, but I think people are moving in my apartment complex here. Okay, so I'm going to stack this. I'm going to take this one, this next piece of the pie, and, no pun intended, next piece of the pie. Okay, I'm going to stack, right? And then I'm going to take this one, and I'm going to stack it. And you can see that if I keep going like this, I get some shape that vaguely resembles, let's see here, that vaguely resembles a big rectangle, right? There's some error, right? Sorry, this diagram sucks. There is some error, right, in the sides of this triangle, like all this space that I'm missing, right? Because these are arcs, these are not perfect. These don't fit. These arcs of this pieces of the pie, they don't fit perfectly in my rectangle. But if I take an infinite number of these triangles, they would fit pretty well, right? They would this error would go to 0 if I in the limit that I take an infinite number of these triangles. And you know that these are all of radius r, right? And you know that the circumference of we know that the circumference is 2 pi r. And so if I do this all the way around the circle, if I keep making these slices, that means that this height, right? This height is just half, right? One of the heights, this is the arcs of only one. See how half the triangles have their arc on this side, and the other half has the arc on this side? That means that this length is half the circumference. This is pi r, right? And now what is the area of this rectangle? Well, you know that the area of a rectangle is just the base times the height. And what's the base times the height? Pi r times r. What is pi r times r? It's pi r squared. So this is a elegant and there's no calculus here. Technically there is calculus because like I've appealed to the notion of the limit and taking an infinite, and this is really, one could do this. Okay, in fact, let's talk about this. For the seniors, so 9th through 11th graders, you can tune out. This is all you need to know. But for the seniors, you're going to learn, especially if you take BC calculus, that you can also do this using polar coordinates, and this is what most people see when they're seniors. In polar coordinates, you can find that the area of a circle is given by, so basically when I'm summing up triangles, right? When I'm summing up an infinite number of triangles, I'm taking an integral in polar coordinates, and that integral would be of over two different coordinates, over the radial coordinate. Remember when we talked about polar coordinates, r and theta? R is your distance from the origin, and theta is how far around you're going. Well, yeah, so you'd be integrating over the radius as well as the angle, and your angle, right? So you put the limits of the, don't worry, this is just an introduction to calculus. This is not, you know that the angle to go all the way around a circle is 0 to 2 pi, right? 2 pi radians are in a circle. We always use radians in calculus. And say that the radius is r, capital R. Well, it turns out if you do this is a double integral, so maybe beyond the scope of high school, but regardless, the inside integral gives you r squared over 2, and the outside integral gives you a factor of 2 pi. And when you multiply these things together, you get pi r squared as well. This is a capital R. So this is the way with calculus, but I like this approach because the 9th through 11th graders can appreciate it, and it's very intuitive. Okay, so this is something you can show off to your friends. You can say that you've derived the area of the circle. And now let's just do some examples. So what is the area of a circle with radius of 5? Well, you literally just plug in the formula. Area is pi r squared. Radius is 5, so this is just 5 squared times pi, which is 25 pi. Okay, that's trivial. What is the area of, if the radius is 1 over pi? How would I do this? Well, I would write area is pi r squared, and then I just plug this in again, same boring process. And this is what I have. And you should immediately recognize that this is 1 over pi because one of the pi's cancels. Okay, so on and so forth. This is trivial. I think you all have done this since 5th grade. But they might spice it up a little by asking you what the area is based on what the diameter is. And so if they're given a diameter, the area is given by pi r squared. So the area is given in terms of the radius. So you need to get from the radius to the diameter. The way you do that is divide by 2. So the radius is 3 pi squared. And then I'd plug this in, right? I've just plugged in the radius. And what is 3 pi squared? Well, now you sort of need your knowledge of how exponents multiply. Can anyone tell me what this is? Does anyone remember the exponent rules? What happens if you have ab squared squared? 9 pi to the 4th, that's right. Yeah, so 3 squared is 9, and then pi, generally b squared, or b to the a to the c is b to the a times c, and indeed 2 times 2 is 4. So, sorry, 9 times pi to the 2 times 2, which is 4. And so you can write this as pi to the 5th times 9 pi to the 5. Good. So you should be able to sort of manipulate your way around. Something the SAT people love doing is they love making you look for the radius. So they'll give you, they'll say, find the area of the circle if the radius is given by some quadratic equation. And this quadratic equation really has nothing to do with circles. They've just cooked this up to make you solve a quadratic equation to find the radius and then put that radius into pi r squared. So this is a 2-step problem the first part is solving this quadratic equation, right? So we need to do this first, and then we need to do the second. So the second part involves putting your area into pi r squared, but first we need to find r. And can someone factor this for me? Can someone tell me? We spent an entire week on factoring quadratics. Who knows how to factor this thing? Or should we just do it together? So the way I taught you how to do this is to write the different factors. So 3r and 1r, and then sort of cherry pick, wisely choose the other factors to give you a desired result. So I think a good option would be maybe what here? 2 and 3, 3 and 2, 3 and 2, right? -3 and -2, because 3r times -3, that's -9r. And when I add that to 1r times -2, that's -2r. This gives me the middle term. And so I know that this is my correct choice, and then I read across. So I assume that everyone is comfortable with this now. This should be under your belts after that week we spent on quadratics. And so this is 0. And now I use the zero product property to solve this equation, and I would get two statements. And so you can see that we're going to have two possible areas, which is actually kind of interesting, right? Because I want to have two solutions to this equation. The solution to this equation is 2/3, right? The radius is 2/3. The solution to this equation is the radius is 3. So my two areas, I'm going to have one area, I'm going to call this R1 and this R2. So my two areas are going to be pi R1 squared, and pi R2 squared. So pi R1 squared is pi times 4/9, right? 2/3 squared is 4/9. Pi R2 squared is 9 pi. 3 squared is 9. Okay, so this is how you would answer such a question. I'm going fast because we're running out of time. I hope this makes sense. And there are two questions on the quiz that are similar to this, where you have to solve a quadratic to find either the radius or the diameter, and then you will plug that into your appropriate formula. If it's asking for the area, you would plug that into pi r squared. If it's asking for the circumference, you'd plug that into 2 pi r or pi d. Okay, so I did have something else to cover, but I think I'll stop here. This is all you need to know for the homework and for the quiz. Tomorrow, we will be discussing some more advanced topics of geometry. And I urge you all to attend because it'll be helpful, but you should have all the information you need now to succeed on the homework. Here is the quiz. I just sent it out. Let me know if you have questions.